Okay, are you seeing my title slide?
Yes.
Okay, good. As Kim mentioned, the topic for today is the OSHA standard for silica in construction, and we'll talk a little bit about its relationship to EM 385-1-1. But before we really get into the OSHA standard, let's talk a little bit about, what silica is and what it does. Um, Silica is the actual chemical composition is silicon dioxide, and it's the most ubiquitous compound in the Earth's crust. So anytime you're dealing with naturally occurring earthen materials, you have a potential for exposure to silica. It's found in sand, rock, mineral ores, um, and so it's found in a lot of different common construction materials, building materials, concrete, granite, soil, asphalt, grout, cinder blocks, masonry panels, tiles, all those things will have varying amounts of silica, some pretty significant, like up to 20, 25% will be silica. And the OSHA standard, and what we're really concerned about today, is crystalline silica. There are other forms of silica. You may have heard the term amorphous silica, much less toxic, much less hazardous than the crystalline form, even though chemically it's the same material. Of the crystalline forms, there are three major ones: quartz, cristobalite, and tridymite. But for most of the naturally occurring stuff that's unprocessed that we'll be dealing with, most of it is going to be quartz. So if you hear quartz, you should immediately think crystalline silica. And the other thing that we're concerned about with silica is we're concerned about respirable dust. Uh, Respirable means that it's small enough that it can reach the deep recesses of the lungs. And that's generally particles that have a distribution that has a cut point of 4 microns in diameter. And the cut point means, you're going to have a distribution of dust, and I'll show a graph in a minute, but about 50% of the particles are larger than 4 microns, and if about 50% are smaller. And that's the size range that we're really concerned with when it comes to crystalline silica. Larger particles tend to be pretty inert and not hazardous. So we're specifically concerned about that respirable portion. Let's talk a little bit about the respiratory system. Um, when you breathe in air, air is always going to have a certain amount of particulate matter in it. And your lungs are sort of like a sponge material, right? So the purpose is that all those surface areas in the deep recesses, what are called the alveoli, these sacs that the bronchial tubes end up in, are there for gas exchange. When you inhale, you have oxygen rich air, and the alveoli have a very thin membrane, like 1 cell thick, and it's in contact with your circulatory system, also very small blood vessels that have about a 1 cell thick wall. And what they do when they're in contact with each other, because they're so thin, they're very permeable. So this is the way your body gets oxygen it needs. It breathes in, the air is rich in oxygen, it permeates through to the blood and gets distributed where your body needs it. Your body, when it uses oxygen, uh, creates a waste material, carbon dioxide, it has to get rid of. That also gets carried to your lungs, permeates through into the alveoli, and gets exhaled. Your exhaled breath is rich in carbon dioxide, so you're moving waste material. And the reason that's important when we talk about the lungs is that as I mentioned, there's always some type of particulate in the air when you breathe. It could be dust, it could be microbes, bacteria, viruses, whatever, foreign bodies. You can't have them reach that alveoli and basically cover up those gas exchange surfaces. Otherwise, your respiration won't work properly. So the respiratory system's designed to kind of filter out those particles from the air. And the way they do this is a combination of physical and biological factors. The physical factors is that your respiratory system is made up of a series of tubes or canals that grow increasingly smaller in diameter and have a very tortuous path. There's lots of twists, turns, branching. So what happens to particles when they have to go through this sort of maze with all these twists and turns? I just recently moved to a community where everyone drives around in golf carts. And these golf cart trails, you'll be driving down, and all of a sudden you'll have to make a hard right turn to go through a small tunnel under a roadway, and then a hard left when you get out of it. The carts can go up to 20 miles an hour, but if you try to go through these tunnels at 20 miles an hour, what's going to happen? I'm going to get impinged on the wall of the tunnel as I try to make that turn, because the inertia, my mass and my speed, is not going to allow me to stay on that trail. I'm going to keep flying the direction I was going, and I'm going to hit the wall instead of making that turn, right? So that's what happens to the particles in your respiratory system. If they're larger, they have inertia, and instead of making the turns with the air molecules, they're going to get impinged on the walls of your respiratory system. And those walls are coated with mucus. So when they impinge on the walls, they get stuck there. And also, you have cilia, very fine hairs that beat in one direction, and that's up. So it's constantly moving that mucus up, back up your respiratory system to your throat, where you either swallow it or you spit it out. But that's the way the body keeps your lungs clean, by kind of filtering out, using that physical and biological mechanisms to remove particles. The problem is that if the particles are small enough, they're going to make those turns. If I'm a butterfly, I don't have any problem going through the cart tunnels here. So the small particles stay in the airstream almost as if they were molecules of air, gas, because they're so small and light. When they stay in the airstream and get into the deep portions of your lung, then you don't have the protective system of that mucociliary escalator, as they call it, because obviously you can't have your alveoli coated with mucus. You won't be able to exchange the gases you need to exchange. So now you lose that protection. So they get in the alveoli. Now there's another way your body has of removing foreign bodies, and that's through a specialized cell called a macrophage, which tends to envelop foreign bodies and then removes them from the system. It takes it back up to where the mucus is, and it can be expectorated. But the problem is that silica particles, the very small ones that get down in the alveoli, can be toxic to the macrophages. And the macrophages die, and they release other chemicals then that form scar tissues in your lung. So forming scar tissues in your lung, it doesn't sound like a good thing, right? And it's not, for a couple of reasons. First thing is, the way your lungs work, it's a pump, right? It expands and brings air in, and then it contracts and exhales air. So if you have a lot of scar tissue going on, it inhibits that natural expansion and contraction that your lung tissue goes through with the help of your diaphragm. So it kind of restricts how much air you can actually breathe in. The other thing it does is the scar tissue takes up that surface area that's normally used for gas exchange. The gas won't go through the scar tissue. So now you have, in addition to the restriction, you have obstruction. You just don't have enough surface area to move the gas molecules in and out the way you normally would do in a healthy lung. So you can see somebody that's exposed to silica over a long period of time, crystalline respirable silica, is going to have scar tissue that will show up in an X-ray and also be demonstrated by reduced pulmonary function on your pulmonary function test. This is what I was talking about as far as the cut point of the size distribution that we're concerned about. And I think I have this slide a little bit out of place, but one of the reasons it's good to understand that is that if you're trying to do an assessment of the exposure to silica, you need to have a sampling device that mimics the size distribution. And we'll talk about that in a little bit. So you might hear in other applications like air pollution monitoring and studies, the terms PM, that's particulate matter 10. PM10 would be a size distribution that has a cut point of about 10 microns. So that distribution has actually more larger particles than what we consider respiratory or respirable. And then you might hear PM 2.5. Well, that's a size distribution that has a cut point of 2.5 microns. So it's smaller particles than what we're talking about. Those people with asthma or other conditions are particularly sensitive to very fine particles. But what we're talking about is a little bit in between the PM 2.5 and PM 10. It's a cut point of 4 microns, and that's the size that we're concerned about with exposure to silica. Okay, so the health impacts include silicosis. This is an irreversible scarring of the lung tissue. It's been known to be associated with rocks and mineral occupations for centuries. Marble cutters, miners have always experienced high incidence of silicosis. It's progressive in nature. Usually it takes a long time to develop, though not always. Results in shortness of breath, cough, reduced pulmonary function, and other symptoms. And what the OSHA standard is designed to prevent or protect against are chronic silicosis, which occurs when you have exposures at lower levels, but over a long period of time. So this normally takes like 10 years to develop. You can't really see it happening. It's so gradual that before you know it, you have reduced capacity. But it occurs over time. But there's also accelerated silicosis, and this results from really high exposure rates for shorter periods of time, 2 to 5 years of exposure, and it's rapid, and the effects can be severe. I was talking to some people, and it's interesting that even though silicosis has been a known hazard for, like I said, actually a couple millennia, this accelerated form of silicosis has actually occurred pretty recently among people who, have or work in the industry to upgrade kitchens. The big thing now is granite countertops and quartz countertops and quartz sinks and whatever. And then there's a kind of a side industry that instead of replacing your countertops, they'll come in sort of like a bath fitters type operation, and they'll overlay your existing countertops with a thin granite veneer. Well, the guys who do that, all the fabrication is done on site because it's meant to match your existing setup, and a lot of it's small companies for the most part, and they don't always have the controls in place. And so NIOSH has looked at this and started seeing people engaged in these activities with this accelerated silicosis because of the lack of the controls and how much cutting there is involved. So it creates pretty high levels of very fine particulate. And then there's acute silicosis, and that can be caused by extremely high levels of exposure over a relatively short time. That's rapid progression. And you'd see this with people that handle silica flour, which is, the base material is a very, very fine powder, and that can lead to pretty high exposures to respirable silica. Other impacts is that include, an increased incidence of lung cancer among silica exposed workers. And it's really interesting. We were talking about this morning, but people who have silica exposure, whether or not they have overt silicosis, have a propensity toward the development of tuberculosis. And we're not really sure what the mechanism is, but we think it has to do with this whole macrophage death scenario where, they're maybe just not available to attack the tuberculosis bacteria. And other mechanisms thought that maybe the bacteria sort of get encapsulated in the scar tissue where the body's natural defense can't get at them, and then they sort of bloom and cause disease later. But I think there's several theoretical mechanisms, but nobody knows really for sure. But it's definitely demonstrated that people with silica exposure have a much higher incidence of tuberculosis, and people with tuberculosis, when you look back on their exposures, generally have more exposure to silica than, non-tuberculosis patients. So it's definitely that correlation. The other thing that it will result is chronic obstructive pulmonary disease. So you have like chronic bronchitis, emphysema, even in cases where silicosis is not diagnosed. So again, exposure to silica, even though maybe it's not an overt silicosis situation, can tend to make people susceptible to COPD. And if you know anyone with COPD, you know how serious of a disease it is, how debilitating it will be, and eventually incurable. There's treatments, but it's really incurable, and eventually causes death in a lot of patients. Another health impact would be heart disease, secondary to the lung disease. Of course, if your lungs aren't working right, your body still needs that oxygen. How does it try to get it? By making the heart work harder, pumping more blood through your lungs, throughout your body to try to get oxygen where it needs to go. That extra work on your heart over time can lead to heart disease. It's also associated with kidney failure with silica, and autoimmune diseases like lupus and rheumatoid arthritis. And again, I don't really know what the mechanism there. It's just a correlation that's been found in different studies. Any questions or comments so far? Okay. Well, OSHA always had a standard for silica exposure, but it used to be just the PEL, permissible exposure limit. And, they found that, well, with some of these, especially with some of the other effects like lung cancer, that the permissible exposure limit was probably too high. And so about 6-7 years ago, they published new standards for silica exposure, which has a bunch of other requirements in it. And they actually published 2 different standards, one for general industry, so it would be for manufacturing, and one for construction. So we're going to focus on the construction standard today.
Hey,
And
Mike.
yeah.
Oh, sorry.
Okay.
I thought you were stopping. Rich Mendenhall had a question about silica, if it resides in coral and limestone, like in Guam or Hawaii.
You know, I don't think it does. And if it is, it's a very low content, because that limestone is really, it comes from coral, and it is mostly calcium. So I don't think there's very much silica. I think we looked at that before, but that's a good question, Rich, and I'll take that as something to check on. But I'm pretty sure we looked at that before, and there's really no significant silica in this, which is unusual, because it's like I said, most of the materials you would run into that come from the earth would be high in silica, or fairly high in silica. But coral and limestone is not really rock. So let's check that out and get back to everyone.
Right. Thanks.
Okay. Okay, getting back to the standard, what this standard requires, the first thing it requires is a competent person. So if you have a potential for silica exposure, you're supposed to have a competent person. And the definition included in the standard reflects the general definition of competent person, right? Somebody that has the ability to recognize hazards in the workplace and has the authority to eliminate or control those hazards. In this particular case, it's specific to silica, so it's somebody who's capable of identifying existing respirable crystalline silica hazards, and has the authority to implement the written exposure control plan, which we'll talk about in a few minutes. This is the outline for the rest of the standard. I'm not going to get into all these sections in a lot of detail. We're going to touch on some of them, but it has specific exposure control methods, which most OSHA standards do not. Most OSHA health standards do not have specific exposure control methods. They say, here's your target, here's your permissible exposure limit. You need to use engineering controls to prevent exposure above that, but they don't tell you actually how to do that, what the control measures need to be. This standard gives you some options, some specific options, which we're going to talk about. And that's why Kim sent that table around. That's table 1. It's the only OSHA standard really like this, that details that, and of course, like asbestos abatement. But most of them do not detail specific exposure control methods. Talks about respiratory protection, housekeeping. Housekeeping is really important when we're dealing with mineral dusts. I've used to work for OSHA, and I had the opportunity to get into a lot of different industries. And I used to see it quite often where the process itself doesn't lead to high exposures, but the housekeeping is so bad, the dust is allowed to accumulate on surfaces, dry out, and then get re-entrained in the air because of physical processes like forklifts going on. You'd have dust accumulating on rafters, on ventilation system ducts, and anything that would cause, vibration or a disruption would then re-entrain that dust. So housekeeping can be really important when you're dealing with materials like this. The standard talks about a written exposure control plan, medical surveillance, and hazard communication. So I mentioned the exposure targets. The permissible exposure limit for respirable crystalline silica is 50 micrograms per cubic meter. So that's 0.05 milligrams, which, if you're familiar with OSHA standards for other materials, it's pretty low. And that's as an 8-hour time-weighted average. And like all OSHA health standards, it requires engineering controls to stay below PEL, and respiratory protection only if those engineering controls are not feasible or during emergencies. The standard also has an action level of 25 micrograms. It's half the PEL, at which time other portions of the standard might go into effect, like training and communication, things like that. And it applies to all occupational exposures to silica, unless you can be sure that the action level will not be exceeded under all foreseeable circumstances. So I mentioned the specific exposure control methods, and this is the table Kim sent around, table 1. But what it says is that when you implement the control measures in table 1, they have to be fully and properly implemented. And we'll discuss a few examples of that. We'll see a few examples of that. Or if you don't want to implement table 1, then you have to actually measure and control the exposures per paragraph D. So that means you have to do personal exposure monitoring and implement other engineering controls if you find that you're over the PEL. So you have 2 options there. So this is the way that table 1's set up. You can look at your table if you want to look at that instead of the slide, but it has a column for equipment and task, and there's specific types of equipment and tasks that it'll discuss. And for each one of those, it'll have engineering and work practice controls, and it'll have respiratory protection requirements. And the respiratory protection requirements are split. If you have an exposure less than 4 hours, it'll say one thing. If you have an exposure more than 4 hours a day, it'll say something else in some cases. Now, the example I have up here is for tuck pointing. This is, grout removal, let's say from a brick building, using handheld grinders to remove the mortar. This is, particularly high exposure activity. You're dealing with a high-speed grinder. It's handheld. It's right near your breathing zones. You're right at the source, so it tends to generate a lot of airborne particulate in the small respirable size range. And so in this case, they would require engineering controls, including commercially available shroud and dust collector system. And in addition, if your exposure is less than 4 hours, you'd have to have a respirator that has an assigned protection factor of at least 10. So that would be a half mask respirator, NIOSH approved. Could be a dust mask or an N95, I should say. That would have an assigned protection factor of 10. But if you're exposed to this operation for more than 4 hours a day, then you have to upgrade the respiratory protection. And again, this is in addition to the engineering controls. You have to upgrade to a respirator with a protection factor of 25. So that would be like an air purifying a powered air purifying respirator, one that has the blower, or an air supplied hood, something like that, or a full face respirator. So again, that was an example, but the whole table set up, some similar, where you're going to list the task and the equipment, the engineering controls, which are mostly either wet methods or a local exhaust ventilation system, commercially available. The notes on the table say, we don't want jury rig stuff, that has no, no backing as far as its effectiveness. So you have to take a look at that. I'm sorry, I keep switching slides here. And then the respiratory protection, and sometimes the respiratory protection, besides being less than or more than 4 hours of exposure, will differ based on whether or not you're doing the operation indoors or outdoors. So you kind of have to really get into the table and see exactly what it's saying. Here's some examples that you might see on your job sites commonly. You might have a masonry saw, stationary masonry saw, cutting blocks or bricks or tile or whatever. And most of these, it's pretty common now to have a integrated water supply, and we should just require that of our subcontractors. Same with like a concrete saw, like you see on the bottom, a handheld concrete saw. They also can come with integrated water supplies. If it doesn't, like the jackhammering operation you see there, you can add water from another source, but you have to remember that it has to be continuous. You can't have somebody sweat the surface and then go to town jackhammering or sawing. That's not going to control the dust. It has to be continuously and trained on the point of operation in order to really control that dust. Okay, so now take a look at the table and somebody tell me what engineering controls and work practices are required if you're doing excavating. You're digging in soil has silica. What respiratory protection is required? So take a look at, I'm sorry, I didn't make the change. It's not page 11. It's page 15 of the document that Kim just sent out, which is table 1. Anybody see that? Just go ahead and unmute your phone and let us know what it says.
You need water spray or mist for dust suppression. Crusher and other points where dust is generated.
This is for excavating?
Oh, it's a crushing machine, my bad.
Says operate the equipment from within the enclosed cab. When employees outside of the cab are engaged in the task, apply water or dust suppressants as necessary.
Okay, so this is something where the exposures aren't expected to be as severe as some of these other operations where you're using tools to, physically grind or crush material, but there still could be some exposure. So Rich, what's as far as using water suppression, what's the standard there? What's the criteria?
I may be missing that portion. Hang on just a second here.
Mike, are you talking about the assigned protection factor?
No, I'm not talking about respiratory protection right now. I'm just saying if you're going to allow somebody to control the dust with the water spray, like to what level are you controlling the dust?
As necessary.
Yeah, that's what it says, as necessary.
So you got just dust control.
Yeah.
Okay. So
you're
it's not
using enough water
very...
not to clog up your system. That's basically it, right?
Yeah.
You don't want to flood your system because now you've got a mess where you've got to, contain with something else rather than the actual jackhammering or that process.
Okay, I was looking for this. Can you see my screen now, the table on my screen?
No.
You can't? Oh, okay. Sorry about that. I didn't switch. But it says visible dust. You see where it says visible dust? So that, again, it's not a real specific standard, but you have to control visible dust emissions with water. Or, Rich, you mentioned an enclosed cab. So if the only one's exposed in the area is the operator, right? He
Yep.
could be in an enclosed cab. But does the table tell you what an enclosed cab means?
No, it doesn't, but I mean, typical standard is you have a filtration system now in most of the new pieces of equipment, and you're supposed to maintain that system, right?
Okay, if
And
you go,
and the seals with the door closed.
right, you're
Windows
right
up.
on, Rich. And actually it does tell you, but it's in the notes at the end of the table. So go to the next page and look at, let's see, look at, it says II right before the 2 there.
Where it says for measures implemented
Yeah.
that include.
Yep.
Oh yeah.
So is everybody with us? Is everybody seeing that on the, this is page 16 of 17. This is the notes to the table. So it has to be, the cab has to be maintained as free as practicable from settled dust. Remember we talked about settled dust, and I don't know how many excavator cabs have you seen that are free of settled dust?
That's part of housekeeping.
Yeah. But it has door seals and closing mechanisms that are working properly, right? So that includes the windows. It has gaskets and seals that are in good condition and working properly. That would be, around your windows and your HVAC system. It also has to be under positive pressure, maintained through continuous delivery of fresh air. Most standard HVAC systems on heavy equipment do not have that. Although I think there are some manufacturers now that are including that since the standard got promulgated. But there are retrofit equipment that will maintain a positive pressure. And also the air intake has to be filtered with MERV 16 or better. So that's basically a high efficiency filter. It's not exactly the definition we would use in industrial hygiene, but it's very close. And of course, it has to have heating and cooling capabilities. And I would add to that work, because if they don't work, you know what the operators will do. So, it has to meet all those criteria for it to be considered an enclosed cab. Otherwise, if you don't have an enclosed cab and you're not wetting, what would you need to do then? Well, then you would need to do the exposure assessments and then apply controls depending on what your exposures are. So, just take a few minutes and look through some of the other activities on that table and operations, and, get a feel for the kind of information the table gives you.
Mike, this is Pete. Could you mention what we were talking about earlier about, ambient dust and grounds people? Dust control.
About the housekeeping and settled dust?
Well, about what we were talking about earlier about whether you need to sample or
Yeah.
If you can keep it to non-visible emissions with water.
Yeah, and that's what we just talked about with the excavating activities, that
Okay.
if you can keep it, use water to keep the visible emissions down, then you don't need to do anything else.
Okay.
Okay, any other questions or comments on table 1? Okay. So as you can see, some of the other equipment that they cover on table 1 are saws and drills and core saws and jackhammers and crushing machines, milling machines, handheld grinders. All right, and this is what we just talked about with the cabs. So you have to pay attention to the details. Besides the thing that we read about the, you know, what constitutes an enclosed cab, there's also details on there. For instance, if you use local exhaust ventilation, how much ventilation you need. It's got to be a commercially available piece of equipment, not, a job-made piece of equipment, that kind of stuff. So again, there's more details in the table and in the notes to the table that we need to be aware of. And like I said, if you decide, or if a subcontractor decides they can't meet table 1, then their only option is to assess the exposure through air sampling, and then implement controls as needed based on the results of the air sampling. And OSHA, as with all health standards, do not accept respiratory protection in lieu of engineering controls. The primary objective is to reduce the exposure using engineering controls, and only use respiratory protection if the engineering controls are not fully effective to bring you below the PEL.
Mike, this is Jim Bob.
Hey, Jim Bob.
Hey, where on earth did you find that guy? On
Which guy?
that photo.
Which guy is this guy?
That guy right there. I want
Why,
him on my job.
You know him?
Yeah, I didn't know if that was on the moon, but I figured the scaffolding gave it away. He's on Earth somewhere.
You mean because he's actually wearing a powered air purifying hood? Yeah.
Yep.
Okay. Actually, yeah, I don't know. I find most of my images on Google, and I'm sure they're in the public domain and not protected by copyright. So, but the reason I put this picture up there is you can see that, when we talk about assessing exposures, we're doing personal exposure monitoring. And the personal exposure monitoring for silica is different than for other particulate matter, where you're just sort of collecting total dust, right? We don't want to collect total dust because total dust has no significance as far as respirable crystalline silica's health effects. We only want the respirable portion. So when we sample for silica, we have to use a size selecting device that eliminates those particles size ranges that are not in the respirable definition. So typically it's a cyclone. There are other methods that you can use, but it's typically a cyclone. So the way the cyclone works is the air enters the cyclone first. It gets spun around the cyclone, and that's action of the air flowing around and coiling through the cyclone causes those larger particles again to impinge on the walls. They don't stay in the airstream. They bounce along the walls of the cyclone until they finally lose all that inertia, and their mass just causes them to drop out by gravity. So that eliminates, and they're designed and manufactured to specifications for the size that you want, the size range that you want. So these cyclones are specifically designed to meet that graph that I showed you. That's like an ISO definition of respirable dust. And once they do that, then it eliminates those larger particles, and the smaller ones that the cyclone doesn't remove stay in the airstream, and after circling around the cyclone several times, gets sucked up into the filter, and then that what lands on that filter is your sample of respirable dust, and that's what we have to have analyzed. The And then another point, I lost it. I'll probably think of it later. Okay. Any questions on respirable dust sampling? Oh, I know what I wanted to say. If you haven't done this before, and you're going to do respirable dust sampling, it's important that you know the manufacturer's requirements on that particular cyclone, because different people make cyclones for respirable dust sampling, but each one has a specified flow rate. So you can't sample at 2 liters per minute, for example, with an SKC aluminum cyclone. The requirement is 2.5. If you vary significantly from the specified flow rate range, then the dust size distribution that you're going to be collecting would be different. It's going to change. So it might not meet the definition of respirable dust anymore. Usually if you sample at too high of a flow rate, it's going to take out even smaller particles. So you're biasing your sample low. If you sample at too low of a flow rate, it's going to allow some of the larger particles to pass the cyclone and get up on the filter. So you're going to bias your results high. So keep that in mind. Just, whoever cyclone you're using, check their specs and make sure you set your flow rate of your pump to what they tell you in order for it to work properly.
Yeah, and if anyone has to do sampling, let me know. Galson has kits set up, and they'll send you all the equipment at no charge as long as you do your analysis with them. So it's a pretty good deal, and they send you everything pretty much ready to go.
Well, this is Bob. The other thing is to remember that with these cyclones, they're very cumbersome for the individual to wear. So you really got to coach somebody on how to wear them and watch them during the sampling process.
Yeah, that's a good point, Bob. And I think the Galson now, they use a different type of size selector now, and it's actually disposable, which I've never actually used, but I know Ted Johnson has used it on some of his sites.
It's actually much smaller and easier to use.
Yeah. So that would be a good choice, but it's probably still flow rate dependent. And if you get, like Kim said, you get all the equipment from Galson, they should have the flow rates set to what that selector needs, but just, double check it. Okay, so you might ask yourself, well, can a subcontractor just hand out dust masks? Well, remember, dust mask has to be, for this application, it has to be NIOSH approved respirators. So N95s, are NIOSH approved respirators, but like all respirators, you have to have a full written respiratory protection program, which would include, training, medical clearance, and fit testing. So fit testing those N95s is another whole topic, I guess we could talk about, but most people don't. They just hand them out. Okay, we've talked about this housekeeping before, and OSHA specifically prohibits this type of cleaning when you're dealing with crystalline silica dust. No dry sweeping, no brushing, no compressed air cleaning. In other words, you're trying to avoid re-entraining that dust in the air. So wet sweeping, HEPA filtered vacuum cleaners, those are permissible ways to control settled dust. We mentioned the written exposure control plan, and on the left you'll see what's required under the OSHA standard for a written exposure control plan. And on the right, I just included what's required by EM 385-1-1. So I think the challenge is to sort of work them both into one plan. You don't need two plans, but you have to make sure you cover what's in the OSHA requirement for compliance and what's in the EM 385 for your contractual requirements. Now, I don't know if you know, reviewers lately have been looking at the APPs and asking for the silica control plan or not. I would be willing to bet that on the NAVFAC jobs that go through the Navy and Marine Corps occupational health group, Bob Hayes will probably want that. But other than him, I don't know if anybody like on the Corps side has been looking at for an exposure control plan. But if we have those operations where there's a potential for exposure, we should have the silica control plan in there. The medical surveillance is required whenever somebody has an exposure or has to wear a respirator more than 30 days a year. And the medical surveillance under this standard is only required every 3 years. I know we're used to doing annual medicals, but because silica, for the most part, has such a long chronic type of progression, and it focuses on the respiratory system, you're not going to see changes in x-rays and pulmonary function on an annual basis, usually. So every 3 years is probably good enough to catch it at early stages, unless you get involved in, you know, one of those things I talked about earlier, like using silica flour where you can have massive exposures. But for the normal construction type exposures, every 3 years would be sufficient. And like I said, the emphasis of this program is on the respiratory system, but it also includes tests for latent tuberculosis, because as we mentioned, tuberculosis is really strongly associated with silica exposure. And then communication and hazards, just, you know, follow what you would normally do for HAZCOM. But OSHA wants to make sure you cover at least these hazards: cancer, you know, lung cancer, silicosis, the immune system effects, that would be like lupus and rheumatoid arthritis, as we mentioned, and training in the exposure control plan and other parts of the standard. And then these were the compliance dates in the standard, but you can see that full compliance was to be in place 4 years ago. So we're well into the compliance, but most of the stuff is already required by EM 385, EM 385-1-1. Don't permit dry cutting, grinding, sanding, drilling, coring, crushing, unless you have a HEPA local exhaust ventilation system, right? So we should be requiring the subs to use wet methods or manufacturer supplied LEV systems. Use dust suppression. Use the RFP application. And Pete, I wanted to ask you, I believe we already have a clause in the RFP application for silica, right?
Yes, we do.
Okay, do you remember what it says?
No.
Okay, neither do I, and I wrote it.
I just checked the
ago.
box. I just put it in.
Yeah, I think it talks about, you know, if you have these type of operations, to make sure that you do exposure monitoring and use engineering controls or something.
It just complied with the applicable standards in EM 385.
Mm-hmm. Okay. And my own personal thing, let's put an end to the dust mask culture, you know. Oh, you got dust, here's a dust mask, you know. We have to do a little bit more than that. So that's my presentation on silica. Anybody have any questions or comments?
Mike, I got one, and it
Okay.
has to do with the TB. Is it and you may or may not know the answer to this because it's probably in some kind of medical literature, but the chance for TB, is that one of those latent viruses that could be, sitting in the soil that's, associated with silica? Do you see what I'm saying? Because there are a lot of the viruses out there that just sit in the soil and wait for somebody to disturb it. And that's one of the, excuse me, one of the bad things that they're looking at now for how to protect people from a lot of these old viruses that we used to have that are sitting in the soil from eons and eons ago. And so it's, it's becoming an issue more and more as we, keep doing a lot of our excavations and stuff like that in the Earth's crust.
Yeah.
So,
well, Rich, that's a good thought. I'm not really sure. First of all, the pathogen that causes TB is a bacteria, not a virus. But that doesn't change your question. I think your question is a good one. But I will say that the information that I've looked at, the incidence of tuberculosis, actually it's the incidence as well as the severity related to silica exposure is not confined to handling fresh soil. You have people that are doing processing and fabrication like concrete, tile, when you're processing that stuff or crushing rock. So I don't know whether or not the TB bacteria lives in soil, but I think there's more to it than just that. You know what I'm saying? It's something, the way silica affects your body, that's predisposing it to infection from the TB.
Yeah. Thanks.
But it's possible that I don't know if anyone else would know the answer to Rich's question, whether or not the TB pathogen resides in soils.
I don't know.
Yeah, I don't know.
I'm not sure either. I just know that it's part of the testing process, no matter what. Because I worked with a company that we did concrete consistently.
Yeah.
So we went through it every year, and we bring testing folks in, and every year they test them for TB. But that's with a lot of other things. I mean, I get tested for psoriasis. I got to get tested for TB. So it's not just there. It's in several different areas where they test for TB.
Yeah, I'm just kind of curious if it's something like, you always see stuff in amber. Is it possible that it's, part of, silica from the sand that's, encapsulating that? I don't know. I'm just very curious as to.
Don't go to the beach anymore.
Yeah, but you're not crushing it up and you're not grinding on it.
Yeah.
Yeah. Okay, good question, Rich. Anybody else have any questions or thoughts?
Mike and Kim, this is Alvin Harbert. I just want to thank you for your presentation. It was very helpful for me on the silica aspect. And Kim, I appreciate the Table 1 information.
You're welcome.
Yeah, that's really helpful. That's the Table 1 is, of course, OSHA standard, but they don't have all the pictures of the equipment the way the AGC put them in there. So I like that. That's a good document to have.
So Mike, this is Pete. I looked up the RFP. So all the RFPs we send out for work that may involve potential exposure to silica, it says subcontractors shall fully and properly implement the engineering controls, work practices, and respiratory protection specified for the task on Table 1 of 29 CFR 1926-1153, where a task presenting the potential for silica exposure is not included in Table 1. The subcontractor will assess employees' exposure through monitoring and comply with the relevant portions of 1926-1153 and EM 385-1-1.
Okay, good. Thanks, Pete. Yeah, that was actually, you know, I did a presentation when the silica standard was first came out, or this version of it. And that was Manjeev's suggestion that we put it right in the contract. So it's in there. So if you guys are, you know, have a subcontractor that you're struggling with, you know, you can always point them at their contract. Any other thoughts? Okay, well, thanks for attending today and being attentive, and good luck.
Yeah. Thank you, everyone. And if you have questions,